All right. Some things that are already on the board. We are working over a field of characteristic 0. Let's call it C. Sometimes it will be convenient to think it's algebraically closed, but it's not necessary. There are some serious names to remember. Hironaka is the person who first proved the result I'm stating, and the result is actually a version of his result, so it's not new by any means for many decades. There are aspects of it in joint work with Bellotto da Silva, Tiomkin, and Vodacek that are new, having to do with foliations, but there's no way I will get to this in a talk to an audience that is not specialized. There's also further work with Quek and Schober on things I don't know, like characteristic P. And I would like to start by telling you about blowing up, which is the right way to learn about blowing up. That is not in Hartshorne, and it's due to first written down by Rees, and then rediscovered many times in the history by Miles Reed, by Fulton McPherson. So it has to do with the deformation to the normal cone. By Vodacek, who calls it a birational cobordism. Same thing, and by Quek and Reed in the generality that I will need. So let's talk about blowing up. How do you blow up correctly? Maybe here. So I'll assume that I'm blowing up a smooth locus on a smooth variety. So J will be the locus I want to blow up, or the ideal I want to blow up on affine space, simplest possible case to consider. And I'll give you the maybe spec. I'll call this Y. This is affine space. And Rees wrote down this algebra. I'll call it R tilde because later on people called the Rees algebra something else. So it's this coherent algebra. So I'll give it a concrete presentation, and then I'll tell you what it is Grothendieck style. So I'll start with a, oh, and leave some space here. Just after each variable, you'll see. So you adjoin an exceptional variable, and you adjoin variables, transformed variables, one for each of the generators of your ideal. Notice the prime. And then you mode out by a set of relations. I'll call it I sub B and I sub B. X1 is equated with S times X1 prime. XK is equated with S times XK prime. And notice the little space I left. I'll write B. This is B for cobordism, language of Vodacek. It is the deformation to the normal cone, spec over Y of R tilde. And I write V for the vertex of this thing. The vanishing locus of the transformed variables. One writes, and then here's the definition of the blowup. I hope There's an issue with the bottom of the board. I hope it will not get. So this is the blow-up. It's defined to be B minus V modulo the natural action of GM. So I should say GM acts fixing V. Maybe I should specify in a minute. So this is the blow-up is B with V taken out modulo GM. Okay, so what is the action? In order to have an action on a graded algebra, I need to know what the grading is, and I need to give each variable its grading. So the grading of xi prime is 1, and the grading of s is -1. So T acts on s x1 prime through xk prime via T inverse s. So s, the exceptional variable, comes with a negative weight, and we note that the way this action can only have fixed points where these variables vanish. So on this locus, in particular, when not all of them vanish, the action is free. So I have the right to take the quotient here in the usual sense of. So in fact, this is a scheme, and okay. You might not recognize this from Hartshorne. So just a remark. So if you want to blow up the wrong way, whenever you have a GM action, you might try to find slices, at least on some open set. So on x1 prime not equal to 0, I can take the GM slice x1 prime equals 1. It's a representative of the orbit, canonically. And on this, what does this equation say? So this says that if x1 prime is 1, then s is x1. And then it follows that, so xk is x1 xk prime. These are the usual, definitions of blow up with charts that you'll see in Hartshorne after you do the Grothendieck abstract thing. These are the usual change of variable things. And of course, moving from one chart to another is hell. We force our students to learn those changes of variables and say, oh, this is easy, but it's not. It's hell, okay? Whereas just working with one GM chart, that's nice, because you have one exceptional variable. You have a transform variable for each variable that you use for the blow-up. And you just need to understand that it's OK to take the quotient by a group action. OK? It's OK. So I have some further goals to do. So I want to tell you what is the global meaning of this. I want to draw a picture, and I want to generalize this. OK? Where should I start? Anybody here is Grothendieck wants the global picture first? Somebody said yes. OK, so let's switch these. Right. So what is R tilde, this is just so I just take the 8th power of my ideal and I call it IA if A is and O if A is negative, right? So this is the difference from what you see in Hartz-on. This is what's known as the extended Riesz algebra. You throw in also the negative part. But that's what enables you to write very simple equations, by the way. You couldn't write very simple equations for proj of a ring. It's just hell. I mean, you have to take ratios, and when you do the next thing that I will do, it will be completely unwieldy. Okay? Leave some space here because there will be a generalization. And V, what is V? Is the vanishing locus of R plus tilde, where R plus is the ideal generated by the positive part. So this is for ideal generated by. Okay? And again, the GM action just comes from the fact that this is naturally a graded algebra. Or I should put here, this is A in Z. Okay, so this is naturally graded algebra, so it comes with a GM action. Okay, so that's the first thing I wanted to do. Second thing I want to do is to draw a picture. I'm doing geometry. Okay, so maybe I should say there's an exercise for the audience. Find at least 2 points of contact with the workshop. And maybe the word geometry that appears in I think it appears in the title of the workshop, that doesn't count because we are. So we're doing geometry, we have to draw a picture. I'll try to draw at least 3 pictures in this lecture. So let's draw a picture of this. No, I think I have to go like this. Okay, yes, I can do this. So first of all, I have in this description here, maybe I can, yeah, in this description here, I have a variable S. And so the variable S is actually a global thing. It's the generator of the thing that you have in degree -1. And the thing that you have in degree -1 is the structure shift. So it corresponds to the element 1. So if you do it, this is a global thing, right? So you have a map. You have a map from this thing, from B, has a map to affine space. So I think we know how to draw affine space. This is S equals 0. And I'll draw here S equals 1. And when you do, what happens when you plug in S equals 1 in this equation? S equals 1 means that xi equals xi prime. So you did nothing on x equals 1. You just have a copy of your favorite, in this case, affine space y. In this case, of course, this is completely general. It doesn't need to be affine space. And here's, I'll call Z the vanishing locus of J. And this is Y. What happens when S equals 0? When S equals 0, what do I have? S equals 0 means that xi equals 0. So this is something living over Z, over the vanishing locus of J. So the vanishing locus x1 through xk. And over each one of these, I have xi prime varying freely. So it's like affine space. So it's an affine space bundle over J. It is, in fact, the normal bundle of Z in Y. Okay? And if I want to understand what V is, I have colors, and everything needs to be in color. So the boring things remain in white, but okay. So V, so this is just Z cross A1. There's no interesting structure on V. But the variables are sort of the other, yeah. The variable here is S, and the variable here are the other variables that don't vanish. No, and the last thing I need to draw, and for which I need one further color. Let's see if is blue. Yeah, I think the blue will work. So it's easy to draw what the action of GM here is. I draw the action from 0 to infinity. T equals 0 goes here, and T infinity is here. So, of course, this is being a cone. This is a bundle. There's an action of T on the xi with weight 1. S has negative weight. So the action, the trajectories are like that. And the trajectories here are like that. So, okay. So this is a picture. This is should be familiar picture of the deformation to the normal cone. If you have read Fulton McPherson actually took the trouble of drawing the picture of what they don't draw, then this is the picture. Fulton's book. No, I'm saying that if you actually sit down and draw a picture, if you are a geometer, it should be. And then if you remove Z and take the quotient, you get a blow-up. And okay, so traditionally you define the deformation to the normal cone using blow-ups. What all these people I mentioned here say, no. The deformation to the normal cone is the fundamental object of study. The blow-up is an outcome. Here it is. It gives you better equations. It gives you better understanding of the structure. And in particular, it will give you a reason why resolution of singularities works. That's my goal. And 19 minutes have already passed. So let's see if I can achieve this goal. The first thing I need to do is generalize, because this is not going to be enough for the way I do resolution of singularities. There's something idiosyncratic here. For the time being, I'll just write it this way. A formal object where I put xi to the power 1 over wi, still called J bar. It has a Riesz algebra, So, okay, so it's no longer an ideal. I'll have to tell you what it is. Okay, so maybe I'll tell you now what it is. It is a monomial valuation. So it's a J bar correspond to the valuation which takes xi. So the valuation of xi is wi. What's that?
Half of the exercise is not done. Of finding contact with the contact.
Can you say that again so that everybody hears?
Oh, I'm just saying half of the exercise from the beginning is now done.
I think you, so monomial valuation is part of your workshop. Okay, so I think I need to start a score sheet. So okay. Let's see if somebody else finds it. Okay, so it's a monomial valuation. And so I'll write this R and I'll give it very simple. Very simple. I still need my red, very simple changes here. So instead of Wi, I have, instead of Sxi prime, I put S to the power. Okay, so this suggests that the Xi don't have weight 1. In fact, they have weight Wi. So instead of putting Xi in degree 1, I put them in degree Wi. Still a graded algebra. Still an action of GM. Still a vertex. The vertex is stable under the action. I can remove it, take the quotient. Now the quotient is not by a free action. If I take the slice, if I take my slice on Xi prime equals 1, I have a residual action. What elements fix this? What elements of T? So the Wi roots of unity fix Xi prime. Therefore, the action has fixed points. And therefore, because I am who I am, I take the quotient in the correct sense. So I take the quotient as a stack. And I'm sorry, this maybe the local chalks are better at the, yeah, it will probably be harder to erase, but so I have to take the quotient as a stack because the action is not free. Why do I not take the coarse moduli? Why do I take the scheme quotient? Because the scheme quotient is singular, and I want to keep my ambient spaces for resolution of singularities as nice as possible. The picture, however, remains exactly the same. The action has weights. This is no longer a vector bundle. This is the weighted normal cone. It's still an affine space bundle, but you work with it, and it behaves as nice as you would wish after you sort of swallow the bitter pill and get well and get stronger. Questions so far about the correct way to blow up in the classical way, and what is the weighted blow up? Oh, I'm so clear. 25 minutes, only. So so your question, yeah. So this has to be okay. So I need to tell you what resolution of singularities. Okay, so I told you blowing up. Almost half the time is gone. What is resolution of singularities? I do embedded resolution of singularities. I have a singular variety inside a smooth Y. That's why I called Y the ambient space. An embedded resolution of singularity is a modification, proper birational. And if X prime is the proper transform, then I want X prime to be non-singular. Or smooth. So the question, so this is what embedded resolution of singularities means. And the question somebody asked here, I'm allowing y prime and x prime to be stacks. In my world, this is not what Hironaka allows, but we have enough tools to take the final result, which is going to be a smooth stack. So its coarse moduli space has abelian quotient singularities, as it turns out, quotient singularities, and we know how to deal with those. So those are easy in characteristic 0. And characteristic P, if the method used here would work, there would be quotient singularities by tame group schemes, which would still be manageable. There's destackification for tame quotients. So for me, this is not an issue. For a standard birational geometry, this is also not an issue because we know how to resolve the coarse moduli space. All right, so this questions about resolution. How do you do resolution? To do resolution, you need a singularity invariant. So maybe it's time to remove not the exercise and not the list, but I think I can go here. I need to so one way to do resolution is to define singularity invariance, something that measures how singular a point on a variety is. And if a singularity has good properties, then it guides you in the process. So singularity invariant is a thing, if you wish, a functor, a thing that's associated to an embedded singular variety in a smooth variety. And invariant, I'll call it invariant sub x, although it depends on the embedding. And I don't care about outside x for the time being. So from the points of x to a set gamma, where gamma is well ordered, no infinite descending sequences. I want this to be upper semi-continuous, so that when things get worse, you get into a closed subset. And you also want it to be a singularity invariant. So it takes its minimum value if and only if the point is smooth. So when I don't work in positive characteristic, I'm allowing myself to use P for a point. That's not quite enough for what I will want. I want it to be functorial. A singularity invariant is functorial if whenever I have a smooth morphism, so functorial for smooth morphisms, étale, open embeddings, but also products with A1 and stuff like that. All that you expect will not change singularities. And if you have x1 inside y1 is just a pre-image, then the invariant over x1 of a point P1 is the invariant over x, over x, over x over its image. Right? So I want the invariant to not care if I do a smooth morphism. So in some sense, it should, yeah, depend on the codimension of a locus rather than the dimension. And finally, I want the invariant to be a smooth singularity invariant. Which is exactly says that the locus where the worst locus, the locus where the maximum value of the invariant, the worst singularities, that's a smooth subvariety. So I have a chance of improving by blowing it up in some way. The locus where the support, where the invariant gets its maximal on X is smooth. The maximum does exist because upper semi-continuity implies that the invariant is constructible, so maximum does exist. I mean, minimum exists because gamma is well ordered, but maximum is not automatic, but constructibility is enough. So the maximum locus is actually closed. So what does this give us? Questions about invariants, and I mean, you can see, yeah.
Just the gamma globally, or is that like you do some ordinal or natural numbers, or?
So the gamma will depend on the y in which I'm embedding. In fact, it depends on the codimension of the embedding in some sense. So of course, I have this, which so if I'm looking at all schemes inside a y of dimension k, the gamma will be bounded by k. But there's a filtration of all possible gammas depending on you'll see it doesn't matter. It feels like I'm doing something wrong, but wait, what do I want to do? I want to state a lemma, and for the lemma, I need a full board. So I think I have to remove the definition of the blow up. I have the picture there, and the picture will suffice for my purposes. So here's a lemma. Assume inv is smooth functorial singularity invariant. And assume given X inside W, let J bar X1 satisfy the following. So I'm assuming that I have a center for weighted blowing up. Remember, a center is a monomial valuation. It's something that belongs here. And assume three things about this center. First, that the support of J is the maximum locus of this function. And second, and this is the hard thing, the maximum of the invariant on X equals the maximum of the invariant on B sub X, B of X. So I need to draw a picture on the picture. So maybe my last color. So the situation is I have an X. Can you see the green? And the X itself has its the degeneration to the, so this is the, this is the normal cone of Z inside X. I'll call it X prime. No, I don't call it X prime. I just call it this. And the whole thing is, so the whole degeneration, that's Bx. Apply the construction to X itself. If you wish, I take the closure of X, sorry, the closure of the pullback of X. So here I have X cross GM. If I ignore this, I take the closure, and that's Bx, okay? And so this is the special condition, so that the maximum, okay? So I stated a condition, and now what the lemma says, then the maximum invariant of the is strictly less the maximum invariant of X. So the blow up with respect to J of X is just Bx modulo GM. That's a substack of B modulo GM, which is the blow up of Y. So what I'm saying is, if I have conditions 1 and 2, if I have a good invariant, I have condition 1 and 2, then the invariant drops. Give me one moment. Give me one moment. And I'll state a corollary, which I will prove. I'll prove the lemma. I will prove the corollary if I have time. Yes? Corollary. If there exists such a thing for all X and Y, then resolution of singularity holds. And then a theorem. So this is the resolution principle. The corollary is essentially the resolution principle. And the theorem by me, Chomkin, and Vodacek is that such exist in characteristic 0. So resolution of singularities, in our sense with stacks, holds in characteristic 0. Now you had a question.
So you said the invariant somehow depends on the invariant. So for X, the invariant is in Y. What's the case for BX?
Bx is in B, or if you wish, B is By. So this is B. The whole thing is B, which is By, which is smooth. Good question. Mark.
What about the weights in that case? Who chooses them when?
So I'll have to, so I'm saying if a weighted center exists, the weighted center defines for me the B. So B is, in fact, B is W sub Y. It depends on the weights. And the Bx depends on the weights. So I need to choose things with the weights. This is the point that Hironaka did not have. He had invariants of singularities which are not unrelated to this. Later invariants of singularity are even more similar to this. I haven't told you what the invariant is, but and well, the invariant, well, okay, you will see. Maybe I don't have time, but it didn't have the weighted blowup as a stack, and therefore it didn't have the resolution principle. It had to work much, much harder. I'll have to choose the weight. I'll have to provide you with the center. This is a theorem. This is not a corollary. This needs to be proven. It takes 15 pages. I think this is better than 200 pages. My sense is that you can read these 15 pages inside a paper of 21 or whatever it is and understand. Hironaka would agree that his paper is very difficult. Okay. So the lemma says, here are the two conditions. If I have a singularity invariant and a center, in order to reduce the invariant. The corollary says, if such exists, then I can do resolution singularities. So let's just wave hands and say why the corollary holds. Invariant drops, and invariant takes values in a well-ordered set, so it has to drop only finitely many times. And the only time when I don't have anything to do is when X is already, I mean, when the center will be empty, when there are no singular points. So X is non-singular. So that's the corollary. For a proof of the lemma, I'll need to use the picture. I will wave hands, but I'll use the picture because I'm a geometer. You guys have not found the second point of contact yet. This is about tropical moduli spaces. I don't know. Wait, I need, where is my deformation? Oh, here's the deformation. I need this up. Okay. More questions? I mean, this is a crucial point. I will feel that I succeeded if the next point becomes clear. All right? So I claim that if I have an invariant that is a smooth functorial singularity invariant, and I have a center whose support is the maximum locus of the invariant, and the maximum remains the same on the whole deformation to the normal cone, then I have a resolution of singularities. Then the invariant drops, and therefore I can continue. So why is that? So first, let's ignore S equals 0. What I have here is Y cross GM. Okay? Y cross GM maps to Y, so the maximum locus of the invariant on B is inside. So let maximum locus. So W intersect with Y cross GM. So that's the open set inside B. Yara calls this B minus. It's a thing whose quotient is Y. And if you remove this, you get the quotient, the blow up. Okay, so W intersect with Y cross GM because of functoriality is just V intersect with Y cross GM. Y is upper semi-continuous, so W consists of the closure of this. I mean, the value here can only grow on this, but it's a maximum locus, so it consists of the closure plus maybe something. So W is V union something in a W prime is contained in S equals 0 in the normal cone. But I'm saying this can't be, because if I have a point here where I have maximum value of the invariant, then because of factoriality, group action is factorial, is a smooth thing. So the entire orbit of the GM action will also have the same invariant. And at this point, W will not be smooth. So there can't be the extra components are empty. So W has to be, so the maximum locus has to be V, the vertex. In the blow up, I take B minus the vertex, I remove this. So the invariant is lower. Let's say that again. This feels like I'm cheating, right? The first thing you learn about resolution singularity is that you are not allowed to erase a singularity. You have to do something proper. That's okay. But here I'm allowed to do that because I'm doing something more fancy. So I'm removing this and taking the quotient. This is what replaces Z, this, not this. So I'm removing the maximum locus. I'm removing the maximum locus. What happens to the invariant outside the maximum locus? It drops here. And now I'm taking the quotient by a group action. Quotient is a smooth thing. It's important to take the stack theoretic quotient. I'm taking the quotient by, so I have a smooth map from what is sometimes known as B plus. So I have a smooth map, and therefore the blowup has the same invariant as the invariant here by factoriality. Invariant dropped here, invariant dropped on the blowup, and I'm happy. Shall I repeat that? If this is all I've done today, I've done more than I wanted. I was happy that I showed you how to blow up, okay? I was happy that I told you that resolution can include stacks, which come from moduli spaces. And I'm now happy that I told you about the criterion for resolution of singularity. So this is it. This is why resolution singularities in characteristic 0 works, because we have a solution to this very clear problem. Find an invariant so we prove the lemma. So all we need to do is to find an invariant and a center that satisfy these conditions. Okay, I think, so I've done what I really wanted to do today. At least some people, I see from faces that some people understand that resolution of singularities in characteristic 0 is achievable. I still have to tell you how to construct this invariant, but even more importantly, I need to give you examples of how this works. Yes, Barbara. So I can construct, I haven't told you how I construct the invariant, and I can construct. So there is a point, a classical point where the construction fails, but I can go around it. I can construct an invariant. It fails already in point 1. Oh, it fails already. It's not, okay, it's upper semi-continuous, the same target group, target set, a smooth, so it's a factorial singularity invariant, but it's not smooth, and it does not satisfy this. Even when it's smooth, it does not. In characteristic 0, I can construct. In characteristic P, I can construct such a thing, but it fails. So this, don't worry, this is just 10 minutes to go. Yeah. In characteristic, so the question that I was asked is what's wrong in characteristic P? And I tried to sort of answer it. That's the work with Weck and Schober, whose names have been erased already. Let me give you examples, and I can wave hands on proofs. I mean, in the second hour of my talk, I can easily show you how to construct the invariant. So it really doesn't take that much. But I think examples are more valuable here. This is, okay, so this is relevant for the second example. Let's do my favorite example, which is the Whitney umbrella. So I'll take x squared minus y squared z. We are geometers. Here's the picture. Do you see the picture? The invariant, so the maximum locus is this. And it has to do with the shape of the equation. X occurs in degree 2, y and z occur in degree 3, so I put 3 and 3 twice. And the corresponding center, so in order to have any success, the center has to somehow align with the invariant. So center, so J, not J bar, is x squared y cubed z cubed. It does not have the shape of J bar because the powers are not inverses of integers. It's still a monomial valuation, but with rational values. I have to rescale it to become a monomial valuation with integer values. Did I drop something there? And then, so the center, J bar, is x to the 1/3, y to the 1/2, z to the 1/2. And let's just see what happens here. So if I take f times OB, remember in B, I have the equations. X is s cubed x prime, y is s squared y prime, and z is s squared z prime. So if you take that equation, you have s to the 6 x prime squared plus s to the 4 y prime squared s to squared z prime, which is the same as s to the 6. That's an exceptional, s is the exceptional variable, times the new, the proper transform is this. So that's a minus y prime z prime. Of course, it looks like the original equation, but something did happen here. What? So why is this any better than what I started if the equation is the same? Zero is gone. Oh, thank you, Martin. I have removed. So what Martin says, I've removed the worst locus in the deformation to the normal cone. And therefore, the remaining worst locus is when z is a unit. You get, I mean, the other loci are smooth, but when z is a unit, you get just the normal crossing intersection. 2, 2 is the invariant, which is definitely smaller than 2, 3, 3. So that's one example. Let's do the second example. And for the second example, I need to do some maneuvering. Ugh. Okay, so the second example is that equation, x to the 5 plus x cubed y cubed plus y to the 100. 100 is just a large integer, bigger than or equal to 8. And then the invariant. Of course, you'll start with 5, and you wonder what the next term should be. So the order of vanishing is 5 at the origin. What you want to put here is what power of y will balance with that. And that's why I drew this picture. So here's the Newton polygon. So there's an assumption here that the variables x and y are already well selected. And so this is the Newton polygon. This is the leading face of the Newton polygon. And if you follow that to its intersection with the y-axis, so the j is x to the 5, y to the 7 to 15 over 2, maybe 7.5. And if you rescale, j bar is again x to the 1/3, y to the 1/2. If you plug in this equation, you get that the equation of x prime is x prime to the 5th plus x prime cubed y prime cubed plus, okay, so y prime to the 100 times s to the 185. So the s appears here. That's because this equation is not weighted homogeneous. So the weighted homogeneous part will remain the same. The part that is on the face of the Newton polygon will remain the same. The rest will have s's in it. But if you remove x prime equals 0 and y prime equals 0, well, when x prime is non-zero, this is smooth. When y prime is non-zero, the invariant is 3,185, which is definitely less than 5,7.5. Because I use lexicographical ordering, as you do in Grosvenor basis, for instance, for the invariants. So this is the second example. And so immediately, so the point is, with weighted blowup, the principle that I had here, the lemma and the corollary say, with weighted blowup, if I have an aligned center for an invariant, the invariant will drop immediately. And a theorem that I have not proven, I have only 2 minutes. There's no way I will show the existence of the invariant and the center. They are constructed simultaneously in characteristic 0. There's no way I'll do it in 2 minutes. But trust me, we can do it in 15 pages. So now you know why, well, at least you have an idea why resolution of singularities in characteristic 0 works, I hope.